Equations of circular motion. Okay, so this is a lesson about the equations that we use maybe for circular motion. We really only introduced really just starters, so we're going to be looking at these equations here. We did introduce angular frequency, angular velocity, which is omega. Angular frequency is something else coming up in another topic. And we can calculate that using 2 pi f or 2 pi over the time period. So we'll go back to where we are. So this is a first little task. Just see, without using any formula, just by thinking about it, as a vinyl album, it rotates at 33 RPM, so that's revs per minute. So you should be able to calculate the angular velocity from that in radians per second with a little calculation. Now you're on a record player and it's moving round, and the record player is the needle is 10 centimeters from the disc. So can you actually calculate the speed, the relative speed between the needle and the record player when it's traveling, when it's doing angular velocity of 33? So have a go at thinking. I'll pause this video and then I'm going to go through it with you. Okay, so let's see what we're looking at here. So first of all, I'm going to calculate what I would call the circumference of our circle that we're notionally going at. So circumference is 2 pi r, yeah, should know that one. The radius is 10, which is 0.1. So the circumference that we're going through is 0.2 pi. I don't need to calculate that. I can just leave that as 0.2 pi meters. It's got a value. Now, the doing 32 revolutions per second. So it's 32 revolutions per minute. So how many are they doing per second? Well, the frequency is going to be 33 over 60. Therefore, the time period is going to be the opposite of that. So that's a time period for one revolution, then opposite the reciprocal, I mean, 60 over 33. Speed equals distance over time. The distance is 0.2 pi, and this is 60 divided by 33. When I now calculate that on my calculator, I'll find out that I get 0.346 meters per second. Now you might have tried it another way, but that's pretty much the answer. Well, I'm going to show you an equation that really sort of just does that in one step for you. So this equation is really V equals omega r. It doesn't really need too much derivation. We can just think about what it means. If we've got here the angular velocity, let's just think I've got an angular velocity of 2 pi, because an angular velocity of 2 pi radians means that you're going round 2 once per second. Well, how far do you travel? How far do you travel in 1 second? If you're traveling angular velocity, you'll travel 2 pi r. If you've got, so really this over here is really telling you how far you've travelled in one time period. In which case, that's going to be your velocity. V equals omega r. So the velocity is really, so this is just going to really in effect calculate the circumference divided by the time and end up with your velocity. Only really works if you're working in radians. You can't use angular, so you can give angular velocities in RPM, in degrees per second, but it only really works, well, it only will work if you're working with radians here, which is a good reason to use radians. So let's put it into effect in this formula down here. Let's see, V equals omega r. Calculate the linear velocity speed of an object in circular motion as an angular velocity of 15 rads and a radius of 14. Well, 15 rads, well, 2 pi, so just do that here, 15 divided by 2 pi equals, this is just a little bit of help for me, 15 divided by 2 pi, what am I doing here, you might ask? I'm just getting an idea of how many cycles I'm doing per second. and it's 2.38 equals 2.38. So this object is really turning around and it's doing 2.4 cycles per second. That's what this 15 rads per second means. V equals omega r, and we're 14 meters away from it, so it's going to be 15 times 14. 15 times 14 is 210 meters per second. So an object that's doing 15 radians per second in a distance of 14 meters will travel in 1 second 210 meters per second. So we could have solved that previous question with exactly the same technique. We could have just done V equals omega, so omega could have come out of here. There's r, so 2 pi f times r, and that would have been given us the same answer. So here's a few more examples. Do you want to have a go at doing them, and then I will go through them. So pause the video if you're working online. Okay. Calculate the angular velocity of an object moving in circular motion that has a constant speed of 33 meters per second and moves in a radius of 72 centimeters. Okay, that's my V, and that's my R. Angular velocity, V equals omega R, omega equals V over R. So omega is V, which is 33 divided by 0.72. 33 divided by 0.72 is 45.8 radians per second. Second one, calculate the linear velocity or speed of an object in circular motion that has an angular velocity of 15 radians per second and moving in a circle of radius 23. Okay. Formula I'm going to write down, no surprise. V equals omega R, which equals omega is 15 radians per second, so that's the same, so that's 2.4 cycles per second. And R is 23. And that gives us an answer of 345 meters per second. So pretty fast if you're rotating around that fast. That's 2.5 cycles on a lever. That's maybe something like a centrifuge that might test the astronauts in or something like that. Calculate the linear velocity of a point on the equator of the surface of the Earth with respect to the Earth's rotation. So what we're thinking here is, what is the speed if you were fixed in space looking down at Earth and the Earth was spinning below you? What speed is the surface of the Earth spinning at? V equals omega R. Now we did calculate omega before for the rate of rotation, but I'll do it again here. Omega, what is, well, every day the Earth rotates once, so that's going to be 2 pi divided by 24 times 60 times 60, so that's seconds and minutes, and then we multiply that by the radius, which is 6.4 times 10 to the 6, don't forget that 6, because that's 6.4 times 10 to the 3, and it's got your kilometers there, so it's 6.4 megameters, though we don't often use that unit. And that tells us that the actual speed that we're traveling at right now is approximately about 465 meters per second, about 1,000 miles an hour. Obviously we don't feel that because everything's moving that speed, so we're not particularly feeling that force of movement. Okay. Well, here's a nice little slide. Now, this is really helps us understand what's going on in circular motion. So please see if you can follow this and watch the video again. An object is going around the outside in a circle. So you've got this. We've got a nice dotted line here, and an object is going around here, starts here, and it's moving all the way on a circular path. Now, we're not really explaining at the moment why it might be moving around on a circular path. We're just saying we observe an object moving around. It's moving around in a circular path, and it's moving around at a constant speed. So what I've drawn here is the vectors of the two speeds. I've drawn v1 for the initial speed and v2, and you can see they're tangential to the actual route that the object is taking, because that's the instantaneous velocity here at one point, and here is the instantaneous velocity at a point a small amount of time later. We'll call that delta t. So what can we look at here? Well, let me show you this little diagram here. Okay, so let's have a look at what I've got in this little diagram here. And what you can see in this diagram here is I've taken a copy of V2. Yeah, there you go, put the V2 back. And I've subtracted, that's why the arrow is reversed here. I've subtracted V1. So that's V1, but it's been turned around on its head, the arrow, because what I want to do is actually calculate V2 minus V1. Which is actually, if you think about it, V2 minus V1 is really the change in velocity. And you can see from this here, the change of velocity, the change of velocity which is going to be used to calculate acceleration, it's actually, you look where it ends up. The overall vector of V2 minus V1 is pretty much pointing in towards the centre. Now, I'm going to ask you to watch another video by this really good video which explains how you can use this vector triangle. And just to show you quite simply, if you look here, you can see this is V2 minus V1. Well, the angle between V2 minus V1 is the same as this angle here, because really that is just the same as that line rotated through 90 degrees, and this is this line rotated through 90 degrees. So the angle between V2 and V1 is the same. So you can actually do a really neat comparison of this triangle with this triangle here. And that's not a perfect triangle, but it's not bad, especially as V2 and as the time distance between those gets smaller. You can almost ignore it, and that's exactly what we do, and we can create a nice formula from that. But what I'm really trying to show with this diagram is that when you're moving in a circle, when you see anything moving in a circle, the actual acceleration is actually, your change in velocity is towards the centre, and it's called centripetal acceleration. It's not centrifugal. That's a bit of a misnomer, that word. You're not being pushed out, you're being in effect pushed in. You might feel that you're being pushed out when you're moving in a circle, but that's the same reason why you feel pushed back into your car seat. If the car accelerates, you get pushed back into the seat because you're being accelerated forward. So it's called centripetal acceleration. And really, this is just an appreciation that this is not explaining why something moves in a circle. This is just an analysis that says what we can say about things that move in a circle. So let's maybe summarize some of the key points here. Explain why an object that is moving in a circle at a constant speed must be accelerating. Well, have a think about it. This object was moving at a constant speed. Was it accelerating? Well, yes, because its speed is changing. Its speed isn't changing, but it's changing. But it's changing its direction, and because velocity is a vector, then the velocity is changed, and so the acceleration is a delta v over delta t. So you can travel at a constant speed, but if you're moving in a circle, traveling at a constant speed, you're always changing your velocity because you're always changing direction. So therefore, you must be accelerating, because accelerating is rate of change of velocity. What do we call it? Well, centripetal, not centrifugal. And what direction is this acceleration? It's always directed towards the center. Always directed towards the center. So please take a minute. I really think this is a fantastic video. It explains in a little bit more detail the mathematics. He's doing a circle, he's doing two objects moving in the opposite way, and he explains how you get to this formula here that we're just about to introduce. You don't need to be able to derive this formula, but this is a relatively simple derivation. It's nice and straight and concise. So have a look at that, and it just might help you understand it. Here's another one. This is from Hyperphysics. It's a similar proof of A equals V squared over R, but I think the YouTube video is much better. Okay, so let's start trying to use this formula. So here's the formula you'll get given on the data sheet. It's A equals V squared over R. So if you want to, you can just accept that as true. That is true. You can follow the derivations if you want. If you use A equals V squared over R and you combine that with V equals omega R, you actually get this equation to drop out. So maybe pause the video and see if you can just do that here. Well, I'm just going to do it now, or you can work along with me. So it's relatively straightforward. A equals V squared over R. We're taking that as our starting point, but V equals omega R. So that equals omega R squared divided by R. Let's do it slowly. Omega squared R squared over R, which equals omega squared R. So those formulas are really just two of the same formulas. Okay. Let's go through these two calculations. If you want to, pause the video or just work through them with me. Calculate the acceleration of an object in circular motion that has an angular velocity, that's omega, of 17.5 radians per second, and it's moving in a radius of 40 meters. So what we're given omega and R. So in effect, I'm going to probably be easier to use this formula here. Calculate the acceleration. A equals omega squared R. Omega has to be in radians, but it is, so that's fine. 7.5 squared times 14. And the answer is, I haven't done this one, so I'll have to go and calculate it. 17.5 squared times 14 equals 4287.5. 4287.5. Well, I'm being a bit silly there with the sig figs, but I'll let you think about why that's so silly. Meters per second squared. Just have a think about that. If we divide that by 2 pi, so what's 2 pi? 17.5 divided by 6.24. So that's spinning around just under 3 times a second, and we're on 14 meters. So, you know, this is a pretty intense situation we're in here. So no surprise to see that's a really large acceleration. You really wouldn't want to be sitting in that centrifuge. Calculate the speed of an object that has a centripetal acceleration of 6.2 meters per second squared and moving in a circle of radius 2.8. Okay, calculate the speed. Well, the only formula that does speed and acceleration is this one up here. So let's start off with A equals V squared over R. That tells us, I'll do this in one step. I think V equals the square root of AR, which equals the square root of 6.2 times 2.8. 6.2 times 2.8 equals 17.36. Square root that. 4.17. 4.17 meters per second. Okay. Just a quick little comment about centripetal force. Clearly, we're still on a position where we're just analysing objects that go around in circles. We're not saying why they go around in a circle at this particular moment. There must be some force applied, but this is just saying if something's accelerating towards the centre, we knew from Newton's law that F equals ma, so there must be a force applied to it. So let's see. force, it has to be centripetal force as well. The force has to be directed towards the centre at all moments. Because of that, otherwise it wouldn't be going in a circle. We know the force has to be because the acceleration is always acting towards the centre. So if we see an object, from what we've already proved, we see an object going in a circle, then it must be accelerating towards the centre all the time. If it's going in a circle at a constant speed, it must be accelerating towards the centre all the time. It must also have a force towards the centre all the time. So the force is always at 90 degrees to the velocity. What does that tell us? Well, in circular motion, there is no movement in the direction of the force. Remember, work done equals force times distance moved in the direction of the force. So there's no work done actually to the object when you move it in a circle. There's no actual work done, transferred. There's no transfer of energy to the object. Not by the centripetal force, at least, anyway. Okay. Another thing, what else can we say about centripetal force? Well, we know that A equals V squared over R, and we know that A equals omega squared R. That's the one that we did from our theoretical proof, and we did that just a little while ago, just by substituting in V equals omega R. Well, if F equals ma, then we get these two equations. F equals m V squared over R, and F equals omega squared over R. So we're going to have a little practice at using those in a little bit. One more slide before I do some questions with you. What causes circular motion? Because so far what we've been looking at is just the theoretical aspect of something moving in a circle. And we said that if something moves in a circle, it's accelerating towards the centre, and obviously it has a force towards the centre. But these forces need to be real forces. There is no, what I often say is there's no such thing as of actual magical centripetal force. Things go in circles because there are real forces acting them. So for each of these, just have a look and see what is the force that is, do you think, is making it go round in a circle. Then I'll just discuss them. You can choose from these ones down here. So a person on a rope swing. So you've got a person swinging on a rope swing at the bottom of the arc. They're swinging forwards and backwards in a circle, in a little arc in a circle there. What's the force? Well, clearly, fundamental force that's making them is a tension in the rope. I would suggest there's a tension in the rope that's pulling them. Same with a conker being spun around on a string in a horizontal circle. It's tension in the rope. What's making Jupiter orbit the Sun? I'm pretty sure most of you got this one. It's gravitational force. If somehow you could turn off the gravitational force magically of the Sun, then Jupiter would just spin off in a straight line into space. A lorry going around a circular flat roundabout. What's creating the force there? Why doesn't the lorry just spin out? Well, it would spin out if there was loads of oil on the road. It would just go in a straight line. It wouldn't get any traction. If there was ice on the road, or maybe it was going too fast. So hopefully you might have spotted, it's actually the friction off the road. The friction is actually providing a force towards the centre of the roundabout. It doesn't mean, none of these objects, that Jupiter is not moving towards the Sun. The person is not moving towards the lorry is not moving towards the centre of the roundabout. It's just going round the roundabout. And a sock going round in a washing machine, so if you look through a washing machine, if it's doing this very high spin, which we already know now from our previous lesson, about 1200 RPM is what a typical washing machine might do. Well, what's stopping it fly off? Well, it's the physical structure of the outside of the drum. It's actually normal contact force. It's normal contact force between the drum, just pushing it back in. There's nowhere for it to go. Same thing if you're on one of those massive big Wurlitzers that spin people round and round, and you get flung. You feel like you're being flung back against the cage. You're not actually getting flung back against the cage. You're actually being accelerated towards, just about similar to that other example I gave about being in a car. When you get flung back into a back of your seat, you're not really being flung back into the back of the seat. You're trying to stay still while the car is accelerating, and the car accelerates you forward. So the drum is not being flung outwards, it's actually being accelerated inwards. Okay, let's have a look at one rather simple calculation here to tie all the formulas together that we've used so far. Mr. Byrne swings a 500 gram mass. Okay, let's just go 500 gram mass on a piece of rope in a horizontal circus. So on a horizontal circle of radius, that's r, the angular velocity omega. Now they're giving it as in radians, but it's 10 pi. It's not 10, it's 10 pi radians. So that's 31.4 radians per second, but they've left it as pi for some reason. That's fine. Here we go. What's the centripetal acceleration? Well, the formula I'm going to go for here is A equals omega squared r. Omega squared r. A equals 10 pi squared times 1.5. So that's 100 pi squared, 150 pi squared, 150 times pi squared, and I'm getting 1480. So let's do 1.48 times 10 to the 3. Okay. Okay, so it's going around. I'm spinning it around 5 times a second, aren't I? 5 times a second. That's on a 1.5 meter rope. So, what's the instantaneous velocity? V equals omega r. It's the easiest one here. Instantaneous. So, is that hit anyone in the face? What space would they? What speed would it contact with? Well, it'll be omega is 10 pi. Radius is 1.5, so that's 150, no, not 150, 10, 15 pi, which is 15 times pi, 47.1 meters per second. What's the centripetal force? Well, we can do F equals ma, which equals m omega squared r. I'm not going to go and calculate omega squared r already because I've already done it. But if that's the centripetal acceleration, then I'm really just multiplying that by 0.5. So I'll do 1.48 times 0.5, which is 0.74. Times 10 to the 3. What is the name of the force that causes this centripetal force? Well, the answer the answer is not centripetal, clearly. What's causing the conker? What's causing this mass of 500 grams to go around in a circle? It's the tension in the string. Okay, just let's look at a few more questions at circular motion before we start taking it a little bit more difficult. So, question 1. A 500 gram mass is being swung around in a circle on a light string of length 50 centimeters. The speed at the bottom of its swing is 2 meters per second. Find the centripetal acceleration required at the bottom of the string. Well, here I've already got the answers down here for you, so let's go through this one. Let's see. Before we start off, acceleration is a equals v squared over r. We could use a equals omega squared r, but we have to calculate omega. We'd have enough information there to do it, but because we use v equals omega r, but as we got v and r already, let's go with that one. A equals v squared over r. V squared is 2 squared divided by r, which is length. This is just being given here to try and confuse you because it's not required, because we're just asked to calculate acceleration. If we were asked to calculate the centripetal force, then that would be multiplying by 0.5 here again, which would be 4 newtons, but it wasn't asked for in this question. Question 2. A 0.2 kilogram mass is being swung around in a circle on a light string of length 60 centimeters. It makes 1.4 revolutions per second. Find the centripetal force. Well, in this case here, really, what are we given here? We've been given omega, but we've not been given it in a standard form. 1.4 revolutions per second. That means 1.4 times 2 pi radians per second, doesn't it? We've also got 0.2 kilograms mass. We're going to need that because we're calculating force. Let's go off. First of all, 1.4 revs per second is 1.4 times 2 pi radians per second. That's our omega. F equals omega squared r m 0.2 omega 2.8 pi from here squared, and the radius 0.6 centimeters gives us an answer of 9.29 newtons. Okay, all still quite straightforward, just popping numbers into the equation here. Again, these ones not so difficult. Calculate the centripetal force. Don't worry, it will get more difficult. It's quite difficult when you have to calculate forces as opposed to just the centripetal force. That's where you'll get confused. So, calculate the centripetal force for a 5 kilogram body with angular velocity 9.5 radians per second moving in a circle of 40 millimeters. So, we've been given omega and we've been given r. So, instead of using F equals V squared over r, let's use omega squared r, and it's going to be, because it's F, it's going to be F equals m omega squared. So, A is the omega squared r. This is really just a version of F equals ma, isn't it? This is a version of F equals ma for circular motion. Put the numbers in. 5 kilograms, 9.5 radians per second squared, and r 0.4. 181 newtons. Very good. A body moves in a circle with a radius 450 kilometers. So that's, just be careful, that's 10 to the 3 here, isn't it? So it's 4.5 times 10 to the 5. The velocity at a point in the circle is 16 meters per second. What is the acceleration of the body towards the center of the circle? So this is just no mass is required here because we're not calculating force, we're just calculating the acceleration. So we've got to choose between A equals V squared over R or A equals omega squared r. Clearly it's going to be A equals V squared over r. A equals V squared over r. 16 squared divided by 450 kilometers. 5.6 times 10 to the 4, 10 to the minus 4 meters per second squared. Okay. Little introduction to where you will start finding things getting a little bit more tricky. Okay, let's read this question. A 600 gram mass is being swung round in a vertical circle on a light string of length 40 centimeters. The speed of the mass at the base of the swing is 1.8 meters per second. Annotate below to make a free body diagram for the mass when it's at the bottom of the string. Find the tension in the string at the bottom. So please hit pause now and try and do the whole of this question on your own. I'm pretty certain if you're new to centripetal force and acceleration, you will struggle and you will get the wrong answer. But let's have a go. Pause the video now. Okay, let's have a look at what we're going to do here. Here's, first of all, some of you might have skipped out the free body diagram because it's just all so easy. Well, it's not. Okay, so that's my free body diagram here. I've done, if this is an object, it's being in a vertical circle. So there's my object in a light string, and it's when it's at the bottom of the string. So it's at the bottom here, and there's my object right at the bottom, and I've got two forces on the thing. So I'm just going to do one working here on the other side. So what do I know the resultant force is? Well, the resultant force, which we're going to do sigma F, is really, well, we know the resultant force is up because this is actually going around in a circle. Okay, could be the other way, not really that bothered. So the resultant force is up, and the resultant force is T minus mg. Can everyone see that? There are two forces on this object. One is the tension in the string, which is upwards, and one is... Now, it's not, in effect, I suppose it's not clear to say, it's not the tension that's causing the centripetal force, it's the sum of the forces. So the tension does not equal mv squared over r, or m omega squared r. It's T minus mg that is m. It's the resultant force on the object. So I can actually say, take this one further, I can say T minus mg equals, let's see, am I giving speed or m v squared over r. I've chosen to use mv squared over r because I've been given the speed. If I've been given the angular velocity, I'd use that. So what does that tell me? Well, I've been asked to calculate t. So t now equals, I'm just going to put m in brackets, mg plus v squared over r. That's just rearranging, so because it would be d equals mg plus mv squared over r. And you can see, in effect, what's the tension doing? Just think about what's going on here. The tension is providing a force to overcome the gravitational force. That would be just really, in effect, a string providing tension that was just stationary. But it's also providing the acceleration, the centripetal acceleration. So the t has to provide both. If we put the numbers in, we'll end up, let's just put the numbers in now. So it's 0.6, g is 9.81, v squared is 1.8 squared, and over r is 0.4. If you do all that right, you should end up with 10.75 newtons over here. There we go, there's my answer. 10.75 newtons. Very good. Okay, so I think this is where it starts to get a little bit tricky, because really a simple situation when we're just asking about centripetal force and centripetal acceleration is easy. They're always going to be mv squared over r, or m omega squared r. The tricky thing is trying to work out what forces might be causing that. And I think it's very much this section here where people are not, they're skipping out this section here where they're supposed to work out, let's see that one, where they're supposed to work out the individual forces that cause the centripetal acceleration. Interesting little thing, extension now we can do here. Let's just look at the Earth. Interesting little fact. So what we see in this diagram is actually, funnily enough, your weight, apparent weight, appears to change. The gravitational force of the Earth doesn't really change, but the you'll actually get lower as your weight will actually decrease as you get towards the equator. Let's try and explain why that is. Some of the force, centripetal force, is being used to make you go around in a circle at the equator instead of flying off into space. The centripetal acceleration is given by 4 times pi, 4 pi squared r squared over t. We'll try and derive that for you in a minute. Really just have a think about what's going on here. You can read this yourself. When you're here, you're going around in a large circle. When you're here, you're going around in a large circle. And if you're going around in a large circle, you must be accelerating towards the center. So your overall, normally when you would draw this, you'd draw a simple diagram and you'd just expect to draw, if you sort of think of someone standing here, you would expect to draw them, you'd have weight and you'd have reaction force. And we'd normally just say, for all intents and purposes, the R and the W are the same if you're stationary, if you're not accelerating. But that's actually not true, because if you're going round at the equator, well, in effect, your W minus your R should be ever so slightly positive towards the center. Otherwise, you wouldn't be able to go around in a circle. So, extension. Calculate the length of time an Earth day would need to be for you to feel weightless when at the equator. Okay, so we're going to do this now. It's a bit of an extension task. Well, what would that actually mean? I mean, if you think of a thought experiment, if the Earth just stopped spinning, I think temporarily there would be in effect, we would probably, the days and nights would just become the same process as a year, wouldn't they, as you went around the sun. you get days and nights. I'm sure there'd be sort of geographical changes and meteorological changes, but I think fundamentally for a little while things will be able to carry on the same. You wouldn't necessarily notice any difference. But really, let's just think what would happen if the Earth started spinning faster and faster and faster and faster. You can think that eventually everything on the surface of the Earth would get flown off. They would just be thrown out into space. Just think of the Earth spinning around super, super fast. The Earth would just literally, everything would just get thrown off. So there must be a point where when you were going around the Earth that you would just be attached to the Earth. Well, when would that be? Well, that would be when your weight was actually providing your centripetal force. So I've done the working here for you already. So look, if your centripetal force, which is m omega squared r, well, this would be the more general one. So m omega squared r would be your weight minus your reaction force. So the limiting condition would be if you could get that, if you could spin, as long as your m omega squared r was less than your weight, then your weight will provide enough centripetal force to actually keep you going round in a circle. The faster you go, the less reaction force you'll get, because now there is a limiting condition. As the faster the Earth spins, then your reaction force, your normal contact force of the Earth will go down, because you need a bigger percentage of your mg to provide your m omega squared r. Well, eventually you're going to get to a point where your reaction force is 0, and that would be when you're pretty much becoming weightless at the surface of the Earth. In which case this formula just, we get rid of r, and this formula becomes m omega squared r equals, so what can I do here? Well, clearly I can just get rid of those two m's. And what does that tell us? That tells us that omega equals root g over r, which equals that, 9.81, 6.4 times 10 to the 6 is the radius of the Earth. Let's take it one step further. Omega equals 2 pi f, which equals 2 pi over t. T equals 2 pi over omega, which equals 2 pi over, there we go, we've got omega from here. Omega is root g over r, so that's going to be root r over g. And t comes out, if you put it in, at 5,075 seconds, which is about 1.41 hours. So if the Earth started spinning at 1.14 hours, the actual our centripetal force required would actually be 9.81. And so we would, in effect, just become weightless on the surface of the Earth. If the Earth was spinning faster than a time period of 1.41 hours, where would the extra centripetal force come from? Well, there isn't anything to provide it. In which case, the people on the surface of the Earth would stop going in a circle and spin off into space. Here's another way of doing it. You could do, I think this is actually, I did this way. It's actually quite, I think it's quite a bit quicker. mv squared over I equals mg. V equals root g over r. So this is the limiting condition here. V equals omega squared r, which equals omega is 2 pi over t. T equals, we can rearrange this for t equals 2 pi over v. And then we could have calculated it from that way as well. So that's what they were doing in the previous text over here, which derives this equation.